And we're today very happy to have Minhyong Kim, who will be speaking on arithmetic topology, path integrals, and the analogy between function fields and number fields. Minhyong, is it all right if we record this talk?
Yes, of course.
Wonderful. And feel free to ask questions at any time. Please go ahead.
Oh, sorry. I should ask the first question then. I didn't know this was about rational points.
Oh, well, this is a series about arithmetic topology.
All right. Maybe everything is about rational points, so it's okay. Yeah. Okay. So I'll thank you very much for the invitation, and I'm sorry, as I said, I'm not going to say anything directly about rational points, but yeah, it probably is at some level. Let me see if I can. All right. Oh, can you see my slides?
Yeah, it looks
Okay,
good.
good. Right. I should also apologize that people have heard some versions of this lecture before. I feel like I have something slightly different to say from before. It's probably the difference is minute, and it's just that senility is creeping in, and I keep repeating myself, thinking it's new. I hope you'll listen with some degree of tolerance. Let's start out with something that's very well known and maybe it's not even directly relevant to the rest of the lecture, but I feel like it's worth emphasizing anyway, because there is some misunderstanding, I think some minor, well, kind of minor misconception around some analogies of A, which when you look at it from what to me seems a better, correct point of view, illuminates quite a few phenomena in number theory. So what am I talking about here? First of all, there's this very well-known analogy between function fields and number fields, right? Anybody working in arithmetic geometry has encountered this notion. And in the first instance, we're just supposed to look at an algebraic number field and compare it to the field of function on, say, a smooth projective curve over a finite field. And of course, we know they're similar. It's also true that there's these geometric objects that are associated to it, which are also similar. The curve itself is similar to the spectrum of the ring of integers inside the field. And well, I feel like it's also important to remember that there are suitable categories of sheaves that are actually where the analogy is even better than when you're looking at schemes or fields. Um, I've been thinking about this issue for at least a few years now. In fact, here the analogy becomes very good sometimes. Uh, right. So, for example, I mean, sometimes you might need various conditions having to do with whether you're on over function fields or number fields. For example, if you are looking at the category of L-adic sheaves for L some different from P, then locally constant L-adic sheaves over the over for a curve over a finite field. If you want an analog of that over ring of integers, then you need to put some conditions like that they have to be crystalline at all the places dividing L, things like that. There are minor adjustments of this sort, but categories of sheaves actually have very strong analogies. So this is sort of a side comment. I'll just go back to Wei. And when he talks about this, he talks about this in various places. And this quote here, I think, is from the letter that he wrote to Simone Weil, his sister. And he says that the analogy between number fields and function fields is so strict and obvious that there is neither an argument nor a result in arithmetic that cannot be translated almost word for word to the function fields. So that's interesting. So here he thinks the analogy is very, very good. And we all know that there are really substantial consequences when you pursue these analogy. For example, Riemann hypothesis for varieties over finite fields, which Weil himself proved for dimension 1 and then Deligne proved in general. I tend to think that things like the Langlands correspondence for function fields, with its very rich panoply of mathematical structures and theorems, is also a consequence of this analogy, and so it generated lots of interesting mathematics. If you look at the proof of the fundamental lemma in the normal Langlands correspondence over number fields, that actually also does use this analogy, because Bao-Chao-Guo's proof does use algebraic geometry over function fields, and there's some curious. I don't know if people have done a different approach now, but initially there was a curious argument of logic that translated the result over function fields back into the fundamental lemma over number fields that people were really interested in. And I tend to think that things like the weight monodromy conjecture for complete intersections proved by Schulze was also a consequence of this analogy, because his theory of perfectoid fields is exactly what enables you to bring the function field result over to characteristic zero local fields. So there are lots of consequences we know of this analogy, which seems to confirm Wei's belief that it's very, very good. But then, so the curious thing comes at the next step, where people often talk about a trichotomy, or sometimes people also fancifully refer to this Rosetta Stone that's supposed to have had these three languages, enabling people to translate hieroglyphics. So what is this about? Well, Wei says in this same letter that in fact the analogy between function fields and number fields, in that analogy, the function field is just an intermediate point linking the number fields and fields of meromorphic functions on a compact Riemann surface. So that's supposed to be what the trichotomy is, and people have written about this in various ways. And, but his sense of the similarity between, say, fields of functions on an algebraic curve and meromorphic functions on a Riemann surface is expressed more cautiously. He says the distance is not so large that a patient study would not teach us the art of passing from one to the other, and to profit in the study of the first from knowledge acquired about the second. Well, now we know that, of course he must have known as well. I'm not sure exactly what he had in mind, but we know exactly what's wrong with this analogy. It's a very simple-minded error in some sense. That is to say, we know that the better analogy is to replace the finite field by the algebraic closure. Certainly, it's since the meromorphic functions are rational functions on an algebraic curve over C that's algebraically closed. To get a better analogy, we shouldn't look at the rational functions on the curve over a finite field, but rather over the closure of the finite field. So that's a simple correction. So in other words, when people talk about this trichotomy, but in fact there are two separate analogies. One is between the field of rational functions on curves over a closure of a finite field and meromorphic functions on a Riemann surface, and then an analogy between a number field and the field of functions on the curve over the finite field, the arithmetic case. And so you could ask, how do you correct the trichotomy then to fill in these diagrams here? So today I'm going to focus mostly on the second thing, right? Although how to fill in this first analogy into a trichotomy is also interesting. That has to do, in most people's view, with Iwasawa's theory. But the second thing is what I will focus on, and then I'll return to after a digression on physics in a little while. Anyways, so how do we fill in this question mark in the second twiddles? So that also is well known, but I will review it. So once again, I'll go back to the geometry, not just the fields. We know that the curve over the algebraic closure of the finite fields is analogous to an algebraic curve over C, which is the Riemann surface. But then we also know that from a more schemy viewpoint, that the curve over the finite field itself is like a fiber bundle over the circle, because the spectrum of a finite field is like a circle. And the curve over the closure is like a fiber of that fiber bundle. That's all the other analogy that we know very well. So in other words, I'm just saying something very simple-minded, that if we look at the curve over the finite field itself, it should be viewed as analogous to a fibered three-manifold, whose fiber is the Riemann surface, say over 1 or any point. Right? So that's the correction that we have in mind as far as the trichotomy is concerned. And so this is compatible with this analogy that Mazur had and other people between the spectrum of the ring of integers and a three manifold. So there, by thinking about it this way, again, as I said, I keep saying it is well known, but there are consequences. So there's one of the consequences that I'm not going to emphasize at all today, but that's underlying a lot of the discussion, is that when you try to define these things called arithmetic topological quantum field theory that I've talked about here and there, you have to remember, it's very important to remember that the curve over the finite field should be a three-dimensional object. So quantum field theory associates various algebraic categories to geometric objects, and so the category that you associate, the object that a theory, a quantum field theory associates to a curve over a finite field should be analogous to the object that you associated to a three manifold. So for example, for a four-dimensional quantum field theory, this curve gets a vector space, and the curve over the algebraic closure gets a category and things like this. So the thinking about this illuminates various confusing aspects of the geometric Langlands correspondence, for example. But anyways, I won't emphasize that, but I'll just mention that underlies the reason, or that is one reason for emphasizing this correction to the trichotomy. That being said, now I'm just going to move on then to the other part of my title. Sorry, no questions. Actually, are there any questions so far? Feel free to interrupt. I probably just said platitudes.
That was very interesting.
Mm-hmm. Yeah. Any comments? Other questions or comments? If not, I'll dive into this digression on physics. Because, of course, I mean, I've spoken about this before, and today I'm going to speak about it in a slightly different way and maybe explaining a little bit more of the physical intuition, because I think it's a good thing for number theorists to know. These things called path integrals have had enormous influence on geometry and topology over the last several decades, at least since the early 1990s, when mathematicians started getting into this paper of Witten on the Jones polynomial, and the original physicist paper relies everything completely on this ill-defined object called the path integrals, and then they suggest structures to mathematicians that perhaps can be defined rigorously. So that's what gave rise to things like this Reshetikhin-Turayev invariance, and lots of developments in the part of algebraic geometry called mirror symmetry. And it seems highly plausible that we can have similar things in arithmetic geometry and number theory as well. So I will give you a brief introduction to the very basic concepts surrounding path integrals. So the beginning of the story, as many of you may know, is that in quantum mechanics you have this thing called Schrödinger's equation. So wherever it comes from, when you have a physical system, the different possible states that the system can be in is modeled by vectors inside the Hilbert space. If you're being very precise, it's actually the projective space of that Hilbert space, but that imprecision is useful. So the state is given by a vector inside the Hilbert space, and how physics give rise to such a vector we won't go into today. That's an art in itself. But of course, physicists are interested in the possible state, but also starting from a state, how does it change with time? And that is given by this equation called the Schrödinger equation. The system also determines a self-adjoint operator acting on the Hilbert space that's called the Hamiltonian. And a state starting from any initial condition in quantum mechanics will evolve according to this differential equation called the Schrödinger equation. So for example, a typical case is where the space of class states is the cotangent bundle of a manifold. More generally, it will be some symplectic manifold. A specific case, which is very, very common, is the cotangent bundle of some fixed manifold, representing the original manifold represents something like position, and the cotangent directions represent velocity, momenta, or it might not be directly the position of a particle or something like that, but it might be the configurations of a field, like the electric field, and then the cotangent bundle represents initial conditions for the electric field, which then evolve with time. Anyway, so that's a typical situation in which this arises, and in this case, this Hilbert space is often modeled as the L2 functions on the manifold itself, if the classical state is cotangent bundle. And in this situation, this is called a quantization of the symplectic manifold given by the cotangent bundle. So this is a typical situation. And then somehow, having represented physical states, is where you try to solve these equations. By the way, the most important case for a lot of ordinary physics is where this d psi dt is, where this is just this psi is just an eigenvector of the Hamiltonian. So that in that case, you view the state as not changing somehow because it just remains inside the same one-dimensional space. Right? That's solving that case. Finding the size that's for a given age, finding the size that are eigenvectors is more or less a large part of practical physics. Like, for example, when you're trying to figure out the structure of atoms or molecules or things like that. And they just try to solve this equation, the eigenvalue equation. Now, however, now going back to this time evolution, the time evolution is very often expressed by an integral kernel operator like this. So in other words, I'm writing this e to the minus iht for the time evolution up to time t, starting from time 0. Right? And that time evolution can be expressed in terms of an integral kernel. I'm not sure about the analysis involved here, how often this can be done. Right? It very, very commonly can be done in a lot of situations. So there's a kernel operator that expresses how things evolve. So in other words, there's this function of two variables, say in this, I'll focus again on this specific case of the cotangent bundle. There's function of actually three variables, time and x and y, so that if you start with some initial condition psi, you get the evolved state at some condition, at some time t, by integrating your original psi against this kernel. So this is a very common situation. So up to here is just pure generalities surrounding differential equations. But now I'll introduce this object called the path integral. What is this about? So it again, sometimes it's ill-defined, sometimes it's well-defined. There's analysis that I'll ignore. But the basic idea is that this kernel function can be expressed as an infinite dimensional integral over path. That's the basic idea. So here I've written the expression, right? What you do is you consider if you to compute kt, at xy, where did it go? What you do is you take a certain exponential involving an object called the action, and you integrate that over all paths. Which paths? The paths that start at start at y, and end at x. So that's what I mean by pxy. These are all the paths that start at y and end at x. And then for each such, there's a function of those paths, sometimes called the classical action. And you take that function of paths, exponentiate it, and integrate it over all the space of paths. And this Feynman's idea was that there was some physical reason for thinking that this represents this kernel function. And if you think about it carefully enough, this represents the amplitude at x of if you start out with the initial condition being a delta function at y. Anyways, so that's the path integral. It's supposed to be this ill-defined integral over a space of paths. We're not even saying exactly what path, what kind of path. So people have debated this for a long time, and physicists are also very flexible about the kind of paths they allow, but they believe some integral over paths of this sort can be used to construct the kernel function. So just to give you an example of what kind of actions are involved here, there's these kind of very well-known things. If you have a single particle, you have an action that looks like this, that captures kinetic energy minus potential energy. That's the typical kind of thing. And for this example, the Hamiltonian function looks like this, and the Hamiltonian operator is some modification of the Laplacian. So this example is good to keep in mind if you want to keep some concrete model. But anyways, so that's the idea. The kernel function is a hypothesis, if you'd like. This can be represented by an integral of that. Now, Well, actually, returning briefly, because kernel is supposed to be like the matrix, coefficients of a matrix, right, representing this linear time evolution. If you look at this expression, that's exactly what it is. If psi is sort of a vector whose components are the various values of the vector of the function, then this is exactly like matrix multiplication. So, if you want to take the trace of that time evolution operator, it's the same as summing over the diagonal, so you get an expression like this. At least in an intuitive sense. And again, sometimes this can be made rigorous. But now, if you look at this expression, that ktxx, that's supposed to be an integral over a space of paths that begin at x and end at x, so it's an integral over a space of loops. Right? But then, we're also supposed to take such an integral, this is the path integral that constructs the kernel, but that kernel function is also supposed to be integrated over x, right? So to express the trace of this time evolution operator, what we have to do is we have to take this ktxx, the integral over loops based at x, and then integrate over x. In other words, we end up with an integral over all loops. So this is the basic way in which integrals over loops arise in quantum mechanics. It says the trace of a time evolution operator like this. Okay, so that's a quick introduction to path integrals. Any questions here? No? Right. So then having told you about these path integrals, I'm going to tell you, oh sorry, maybe I'll just skip this. There's also a Euclidean version of it, but we don't need this right now. I'm going to introduce a slightly twisted version of this in order to apply it to this arithmetic topology viewpoint that I introduced at the beginning. What is the twist? Well, suppose instead of integrating over loops, we just observe that maps from the circle to some manifold sigma, right, are just sections of the trivial bundle, right? So can I also do an integral over the sections of a non-trivial fiber bundle? Yeah. Say a three-manifold fibered over a circle. How do we interpret something like that? Is there a quantum mechanical interpretation? So there is, so I'll explain that to you right now. So here we go. Given any fiber bundle, let's say we're in the category of C infinity manifolds or something, then it's diffeomorphic to a mapping cylinder like this. So in other words, you consider the monodromy operator as you go around the circle, starting from say 1, the fiber over 1, and then there's a monodromy transformation. Of course, there's a bunch of choices involved, taking local trivializations and so on, but the homotopy class or diffeomorphic isotopy class doesn't depend on the choice of trivialization. So there's a well-defined isotopy class of diffeomorphisms that represent the monodromy of the fiber bundle around the circle. And then your manifold is diffeomorphic to a mapping cylinder. In other words, you just take the product of 0t comma the fiber sigma, right? And then you identify, you glue the end sigma to the beginning sigma via this monodromy map. So that's one way of representing fiber bundles like this. But once you've done that, it's not so hard to write down what you mean by sections, or concrete expressions for sections of such a fiber bundle. That is to say, the sections can then just be identified with maps from the interval to the fiber sigma, right, with the property that the end point and the beginning point are related by this monodromy transformation. Right? So that's clear, simplified the way you are describing this M. So you just think about maps, five sections of this as sections of this trivialization 0t comma sigma with this compatibility with the monodromy map. So this is a way of writing down the space of sections. Right. Then an integral over the space of sections would be something like this. You take this exponentiated action, right? But now you're integrating over the space of paths from x to f inverse of x, right? That's what the endpoint is supposed to be according to this formula. And then you integrate over all possible beginning points, x. So this is an integral over all sections. Now, another way of thinking about it, however, from the point of view of quantum mechanics, remember this integral over path going from x to f inverse of x was exactly the kernel, integral kernel of this time evolution operator, when the ending point again is f inverse of x. Well, actually, this is the kernel when we're started. The initial condition is at y and ending at x. That's what we're substituting f inverse of x for y, no, for x and sorry, x for y. Sorry, that's very complicated. Anyways, I think you know what I mean. So this is an integral kernel for this time evolution operator. Now, on the other hand, if you look at the way, I just wrote it here. If you look at this expression and the role of this diffeomorphism f, well, that diffeomorphism also acts on functions in the natural way. F psi at x is just psi at f inverse of x. So if you think about that formula, suppose instead of taking the time evolution operator applied to psi, suppose we also apply the diffeomorphism to it. That will be this time evolved psi applied to f inverse of x. But then, according to that path integral formula, you just get an expression like this, right? Yeah. So now, if we want to take, so therefore, in fact, we see that the original integral kernel shifted by this diffeomorphism f inverse is just the integral kernel for this operator f composed with time evolution. So what do we do with that? Well, you see that therefore, if we take the trace of that, right, we're supposed to integrate the kernel evaluated at x comma x with respect to x, but then that kernel is represented by this path integral over the space of sections. So what am I trying to say here? So to sum that up, when you try to integrate over the space of sections of a non-trivial bundle, right, instead of just getting trace of a time evolution operator, you get the trace of the monodromy operator followed by the time evolution, or the other way around, the time evolution operator followed by the monodromy operator. That's the interpretation of the integral over a space of sections. There we go. Now, the last thing I want to say in relation to this excursion in quantum mechanics, into quantum mechanics, is that there's a collection of physical theories that are called topological theories, and I'm not going to go into that right now, so that's where somehow you don't depend on metrics. That's the basic idea, that this action and the quantum mechanical operators all are independent of metrics. But without going into those generalities, one consequence I would mention is that for topological theories, the Hamiltonian of the theory is just zero. So that's one key property that it has. So this action is supposed to only depend on the topology. By the way, so people say theory, but when a physicist says theory, most of the time they just mean specifying this action function. Then that's what they mean by a theory, whatever expression they give to it. But then that determines this Hamiltonian, and for a topological theory, the Hamiltonian is zero. That's the general principle. But if the Hamiltonian is zero, then we get this simplified version of this formula for the trace. So it's just a trace of the monodromy becomes an integral over the space of sections. So that's a very nice, neat formula that somehow relates this physicist path integral to the trace of a monodromy operator. Okay, good. So any questions here?
So is there any connection with these path integrals and the modular symbols of monon?
So so modular symbols, of course, are these integrals over from cusp to cusp on things like upper half plane, right? You can certainly that's interesting. You can certainly include modular symbols as paths that occur inside path integrals. But I really like that question, because you see that is kind of the question, the viewpoint I'd like to encourage. There are well-known objects in number theory, like you just said, right? which maybe can be inserted into this framework and about with which we can do interesting things. So of course, as you can see, the short answer to your question is I don't know, but that sounds like an interesting thing. So integrals of the sort that we're already used to, can we insert them into this broader theory? Thank you very much. Other questions? If not, okay, so I'll move back to number theory. Oh, sorry. I mean, do I want to say something about this? And I did prepare one more slide. Yeah, maybe I will say something about this, although I don't strictly need that. So I already pointed out that for a cotangent bundle of a manifold, it is viewed as a space of classical states. Its quantization is the space of L2 functions on that manifold. There are other ways of constructing equivalent Hilbert spaces in some suitable sense, but there's this whole machinery of quantization which people would like to believe as kind of a functor. It doesn't always work in that way, but that's the general desire that you like to realize whenever possible. And on another special case of that, which is actually quite nice and is closer to people like us who work more on algebraic geometry, is that if your space of classical states is a Kähler manifold, when you have a symplectic Riemannian and complex structure in a compatible way, then they often have something called Kähler geometric quantization, where the space of Hilbert space is constructed as the space of holomorphic sections of a line bundle. So that's a kind of an interesting connection to algebraic geometry, which is used in various ways, maybe not as actively as it should be. But what's interesting is that you get holomorphic sections rather than L2 sections or things like that. But so the line bundle itself even may be trivial, but its construction is quite interesting. So one example is if X is just, if your space of classical states is just R cross R, just one-dimensional position and one-dimensional momentum, by viewing it as C, as the complex numbers, you can construct the Hilbert space of L2 functions on R. You can reconstruct it as the holomorphic L2 functions on C. So these are, of course, if you're an analyst, you'll say any reasonable Hilbert space, any two of them are isomorphic. But what happens is that they are isomorphic as quantizations in some sense. But the precise sense is that something that will come up in a very informal way later in a later slide. They are isomorphic as representations of some Heisenberg group. So there's this holomorphic construction of quantizations, which is sort of familiar to people like us and useful. But anyway, this isn't so important for our lecture today, so I will move on. Okay, so now let's return to this number theoretic trichotomy. I've already stated it. If you take a smooth projective curve over a finite field, it should be like three-manifold fibered over a circle, which is then is like one of these mapping cylinders. Here I've used little f instead of big F here. So. Or put differently, we could think of X itself as being constructed as a mapping cylinder from X bar, cross 0, 1, although non-existent interval, or using a monodromy transformation given by the Frobenius operator. But that's also true, of course, for the Jacobian. The Jacobian, it's defined over the same field, but it can be viewed as Jacobian over the algebraic closure, then twisted using this mapping cylinder construction. This Jacobian, by the way, especially over the Jacobian over the algebraic closure, is often arises. So as you know, over the complex numbers, there will be returning to my mild correction of A, J bar is the thing that will be analogous to the Jacobian over the complex numbers. And that really is a Kähler manifold over C, as you know, and this is a state space for all kinds of quantum field theory, especially something called the Abelian Chern-Simons theory that I've been studying a lot. So these arise very naturally when you think about physics in this context. But anyways, J itself is a mapping cylinder arising from J bar according to this analogy. Now, what I'll do is I'm going to first construct a Hilbert space out of this. and then do something with it that hopefully you find interesting. What is the Hilbert space? Well, Hilbert space, I really mean something over the complex numbers. Well, what we do is we take the curve x and we lift it to characteristic 0 over the fit vectors. As you know, any curve can be lifted. And what will happen at the end is the construction will only depend on x bar rather than x, but it's okay. Let's start out this way because to fix ideas. Then, starting with this lift, you construct its Jacobian. That's what I'm denoting by AY. That will be an abelian scheme over W. And then the construct a line bundle. I don't know if this is standard terminology. I'm calling a theta line bundle any line bundle that gives a principal polarization of JY. Now, the next step, it would be nice to do something very uniform without making all these choices. But for now, for today's lecture, I'm going to fix on odd prime, and for some reason I'm calling it n, with the property that Q is congruent to 1 mod n. So this property will be used in various places, but in particular, notice that the nth root of unity is inside our finite field now because Q is congruent to 1 mod n. Now with this, what I mean by the Hilbert space, a quantum Hilbert space in some sense, is the space of global sections of this line bundle raised to the nth power tensored with C. So because of this tensoring with C, so of course this involves some constructions, right? I need to embed W into C and do that kind of thing, which some people don't like, but anyways, I'm not going to worry about that. But you can see that because of this tensoring with C, the construction will not depend on X, but only on X bar. So that's a complex vector space, a finite dimensional complex vector space. I'm not going to emphasize that here, but it's also possible to put on this natural matrix so that it really is a Hilbert space. And from the point of view that I briefly alluded to on that slide that I'm claiming is not important, it is kind of a geometric quantization of the Jacobian. In fact, it will be the geometric quantization of the complex points of this Jacobian, even from a standard viewpoint. But from our viewpoint, what's interesting is there's another interpretation of this as a quantization, which is that, sorry, maybe I'm putting too much stuff on the board, on the slide at once. But anyways, this vector space of global sections is acted on by a finite Heisenberg group with center given by the roots of unity. This action, maybe I won't describe it today. This is in Mumford's book on abelian varieties. I think many of you know about this. So what is the Heisenberg group? The Jn torsion of the Jacobian is a symplectic vector space given by the wave pairing, right? And then you cross that with the roots of unity as a set, right? But then the group structure uses the wave pairing according to this formula. So that's the Heisenberg group. And this will act on the space of global section. That was the point of taking the nth power here in order to make this act. So it is a representation of this Heisenberg group, and in fact it's the unique irreducible representation of this finite Heisenberg group with this the root of unity acting via the identity character as scalars. So there's this something called the Stone-von Neumann theorem that started out with Heisenberg groups over the real numbers, but then other people proved various finite group versions of it that gives you uniqueness theory of this, but once you fix a central character. So you can, and for in this situation, it can be constructed as the global sections of this line bundle. So then from this point of view, the space of this Hilbert space is not necessarily the quantization of the Jacobian, but it's actually the quantization of this symplectic vector space. So remember, I said the space of classical states in physics tends to be a symplectic manifold, and then you quantize it. The simplex case is where you have a symplectic vector space. In that case, the quantization is this irreducible representation of the corresponding Heisenberg group given by the Stone-von Neumann theorem. So here we're not over the real numbers, but we're aware of, we have this, nonetheless, we have this symplectic vector space over a finite field. And because of this fact that this vector space is the irreducible representation of its Heisenberg group, it should be viewed as a discrete analog of this quantization of symplectic vector spaces over the reals. But this Jn, by the way, we also know there is a finite group scheme, right? In fact, oh, no, I forgot to say that. I'm getting my slides mixed up a little bit. But the less trivial fact is that this vector space also admits an action of the finite symplectic group of this symplectic vector space. So that's again a general fact about these Stone von Neumann type theorem, that when you have these irreducible representations of the Heisenberg group, the symplectic group will act on it. But except there's a difference over the real numbers, the action is a projective action, but over a finite field, it turns out to be an actual action. There's a non-projective actual action of the symplectic group of Jn on this unique irreducible representation of the Heisenberg group. But we've set things up in such a way that this Frobenius operator acts on Jn by symplectic transformations. Well, actually, it acts, again, this is over the characteristic 0, but remember, n is prime to the characteristic, so it's the same as the n torsion over the finite field. So the Frobenius acts on it, but also we've arranged it so that Q is congruent to 1 mod n. So, in fact, well, it would normally be symplectic similitudes, but it actually acts by symplectic transformation. So, therefore, the Frobenius also acts on this Hilbert space. And so we can take its trace. So this is something that I came up in discussions with actually VaNTAGe long ago, but actually, of course, has much more difficult things he's working on, and I'm stuck at this very elementary state. So together with my student Yan Yao Cheng, we've refined the formula I discussed with Akshay a little bit. So the theorem is that when the Frobenius action on Jn is semi-simple, and if Fq contains the square root of -1, then the this trace of this Frobenius acting on the Hilbert space will give you essentially the square root of the n-class number of x. So that's the formula. So it's an amusing formula in many ways. Well, this square root is coming up, and square root of class numbers don't come up very easily. This problem of determining this sign is also very interesting, and Yan Yao is working on it right now. But for now, I'll just put that forward as an interesting formula to think about. And the other of these assumptions we should be able to get rid of, but it's a bit tricky. So I was going to give you a sketch of proof, but I see that I'm not doing that well on time, so I'm going to just skip the proof for the moment and move on to path integrals. So far, we've forgotten about path integrals, right? This is the analog of the trace of monodromy, right? The trace of monodromy part that I mentioned earlier. And instead, I'm going to move on to path integrals of a very curious sort. So we'll move over through this. So what is the path integral? Well, so it's like this. So once again, I'm just going to remind you of this simple-minded trichotomy again. Your curve over the finite field is supposed to be like a three-manifold, and the Jacobian is also supposed to be like a manifold fibered over the circle. But that means that even if we take the n torsion of the Jacobian, right, that's a finite group scheme, and that's also like something like a manifold fibered over a circle. Okay. So we can consider its sections. So in other words, the FQ points of that group schemes are like sections of this fiber bundle, right? So what I would like to do is define an action on these sections of this non-trivial bundle over the circle and then integrate. What is the action? So So I'm a bit confused about this. Well, I'll describe it to you and then we'll discuss it about the history of this action. I think this comes up among people who study Galois module structures of rings of integers and things like that. But I'm not completely sure about the relation. But anyways, so it's very easy to describe. So here's an arithmetic action that's defined on the space of sections. So remember, this is supposed to be like loops. I'm going to define an action because this spec FQ is supposed to be like a circle. So remember, this Zen mod n is trivial. Is a trivialization. The roots of unity are trivialized, so it's actually the same. But I'm going to emphasize them then for a reason that will become apparent in a second. What is this action? Well, it's like this. So if you look at the points of the Jacobian, these are also degree zero cycles on the curve. And there's a reciprocity map from geometric class field theory that goes to the abelian fundamental group of X, but except that superscript 0, meaning the geometric part of it, the part that there's a map from the abelian fundamental group to the Galois group of the base field, and its kernel is what I'm denoting by pi 1 abelian superscript 0. And the degree, of course, the Chow group itself will map to the whole pi 1 abelian, and this degree 0 part will map to this kernel. So we can take the n torsion, and there's still a map of n torsion parts, right? So there's a reciprocity map from the n torsion of the Jacobian to the n torsion of the abelian fundamental group. But you see, if you take a class, an n torsion inside the Jacobian, it also defines a torsor on the curve, a Zen mod n torsor. Why is that? Well, it is actually rather simple-minded. It's because there's also an n torsion line bundle on X, right? So what we do is we choose a trivialization of the nth power of the line bundle, then that determines the Zen mod n torsor. Simply those y's inside L whose nth power go to 1 under this trivialization. Okay? So that's a Zen mod n torsor. It depends on your choice of X, or choice of F, choice of trivialization, but that choice, the ambiguity of that choice goes inside this quotient. I'm actually taking h1 of X mod out by h1 of spec of FQ. So that's the choice of F that goes into this quotient. So that's why we're taking the quotient, that is. But this h1 of X is also just Hom, because this is trivial now. The coefficients are trivial. These are just Homs from the abelian fundamental group of X to Zen mod n. So now it's clear where we can get an action. There's a function of the sections given by just taking this cohomology class, this torsor class, C gamma, and evaluating it on the image of the reciprocity map. Now, this C gamma is a class inside this quotient, but the contribution of this H1 of spec FQ goes away because this reciprocity map takes values inside the kernel of the map to the Galois group of the finite field. So this is independent of your choice of C gamma. Okay, so that's a quadratic function. So it takes a little bit of work to show that this is symmetric, for example, but anyways, I'll skip that for today. So you get a function of sections of the Jacobian fibration, the n torsion of the Jacobian fibration, using the reciprocity map and this torsor interpretation. That's a quadratic function. And so we can form a path integral. Oh, sorry, I made a slight misprint. This should be a sum over J n FQ. I'm only going over n torsion. Of course, there's a way to take a limit over n, but it's a slightly, there's some subtleties there, so I'm only going to discuss the sum over n torsion points today. And so here's a formula, which is a modification of something I'd done with those authors a few years ago, and that's implemented by something that Yan Yao did. So it's a lot of, yeah, so again, there's a misprint. This is sum over JFQN n torsion. What you see here is the square root of the n torsion inside of the number of points inside the n torsion of the Jacobian. This is the determinant put inside the Legendre symbol. And this is just a sign, but you see that this is well defined. This is a quadratic form. It's not a matrix, so you might wonder about the determinant. As you know, for a quadratic form, determinant is only well defined modulo square, but it's okay because it's inside the Legendre symbol. And then there's a power of I over here. But with our assumption, this is also an even power. So this is all just a sign. Everything here is just a sign. And then there's the square root of the n torsion inside the Jacobian, which is the n part of the class number of x, right? So the point of all this is that, in fact, you have this path integral formula for the trace of the monodromy operator as we had in the topological quantum mechanical situation. So that's essentially the kind of amusing formula that seems to arise from this analogy and this trichotomy style analogy. The proof is not hard, but as I said, this nailing down this sign, I think, is a very interesting issue that Yan Miao is thinking about right now. There seem to be lots of interesting subtleties there. And I should also say that the proof of the left-hand side, the square root formula for the left-hand side, is a little bit trickier. The right-hand side is, in some sense, it's easy. There's a result of Neretin. There are people who worked on Gaussian integrals over finite field for vector spaces over finite field, and it's a fairly simple consequence of that. Yeah. And you'll notice the analogy with Gaussian integrals over the reals, where you have the square roots of determinants and powers of pi coming up. So it's very similar to that. But one interesting thing is that, so what proof am I talking about? I'm talking about the proof of this formula, is that you can easily reduce it by diagonalizing this quadratic form. You can reduce it to the one-dimensional case. So that what looks like a rather mysterious formula here is relatively simple. The reduction to the one-dimensional case is simple, but there's still a slightly elementary, well-known and elementary but mysterious ingredient that goes into this formula, which is namely this. So unlike this Euclidean Gaussian integral over the reals, what goes into there is this well-known formula for square roots of various numbers as exponential sums. I forgot whose formula this is, but anyways, there's this way of expressing sums of roots of unity, taking sums of roots of unity and using that to express square roots of various discriminants, for example, right? So that's what goes into this Gaussian integral, this path integral formula from the previous slide. So there's lots of little interesting interactions between what seems like the kind of constructions motivated by physics and fairly classical number theory that seems to me anyways fun to think about for people in arithmetic. Okay, I think I'll just stop there today. Yeah, thank you.
Thanks so much. Well, this is a great time for questions. Does anyone have a question? Maybe I'll start with one. So are there, if you apply your formula for examples where the number of n torsion points over finite fields are known, what have you done that at all?
No, I haven't. Yeah, no, that's interesting. Yeah. So yeah, this kind of, so it's a kind of exponential sum formula for roots of class numbers, right? And yeah, it would be very nice if there were applications of it.
Oh, yes, Noam, would you like to ask a question?
Oh, I know.
Yeah, hey there. Sorry, I'm off video, but that was a great talk. I was wondering, not exactly directly what you were talking about, but related to the path integral formalism, I guess. I've always sort of wondered whether there's a connection between the finiteness issues that you have in path integrals, like the large spaces of paths and such, and the finiteness issues with like the things on the other side that you have in the arithmetic, like SHA. Is that something that you see as connected, or is it unrelated?
Well, I don't have a good answer to that question, of course, but if you, have you seen my paper with these other authors on p-adic functions and path integrals?
I've seen it, but I haven't read the entire thing.
Yeah, well, maybe you can take a look at that and we can discuss it later. There's some issues of that sort come up because there to define the path integrals, you're taking some horrible limits, but of course they're finite exactly because people know things like the main conjecture and so on. So,
Oh, cool. Okay.
so there you have this rather infinite looking path integral. And they're a priori. Now we know it's obviously finite. We set up in such a way that it's obviously finite because we have all these facts. They wouldn't have had to be finite a priori unless other people had proved these very difficult theorems.
Great. Okay, I'll have a look at that. Thank you.
So we can discuss that later. But I should also point out it's a kind of a very simple thing, but one amusing thing is that when you're thinking about, so I pointed out that this quantization is the quantization of the n torsion of the Jacobian, right? But the n torsion of the Jacobian is also, the number theory, you don't always think of it that way, but it's just a discrete approximation for this complex torus, right? As n gets large, this will approach the complex torus itself. So you might wonder whether these kind of quantizations are related to the quantization of the continuous objects that physicists are actually interested in.
Wonderful. Let's thank Minhyong again.
Okay, well, thank you very much. Oh,
And
there seemed to be one question in the chat box.
oh, okay. Would you like to? A question about motivations to number theory and applications in number theory.
Well, I mean, can you explain why a number theory should care about it? I mean, you care about what you want. I don't know why anybody else should care about this, and I don't know. I myself care about it sometimes, and other times not much at all. Right? So it's hard to say. But if I were trying to be propagandistic, what I would say is that thinking about these kind of things, I said this at the beginning, but I'm repeating myself. Thinking about this kind of structure, especially how can this very strange idea of a path integral, which is almost like a metaphorical construction as far as mathematicians are concerned, right? And so they don't make any sense. Or rather, okay, maybe I'll digress to a brief philosophical comment, right? So you probably know that for physicists, any of the interesting quantities, if they just computed, give you infinity. If you just start from the bare theory, like quantum field theory of the simplest type, electrodynamics, which governs a lot of, which is supposed to be the most amazing and accurate theory of physics there is, if you just compute from theory, you get infinite. And then they have to go through a lot of modifications to get finite answers out of it. So I tend to view this situation in physics as sort of like Zeno's paradox in ancient times. Because what did Zeno have? He had this situation where somehow he was calculating, this is the legendary Zeno, of course, we have no idea whether such a person existed or they ever said such a thing, but you had this situation where the arrow obviously reaches the target, right? But if you compute it in a certain way, it seems to be take an infinite amount of time. And that's the situation in a lot of modern physics. Obviously, there are finite probabilities associated with certain outcomes of experiments. But if you just calculate it according to the theory and summation rules that we know about, you get infinite. So then they have various, what to me look like ad hoc procedures for fixing this. So in other words, there are certain kind of infinite sums for which we still don't have a theory, although the theory that Zeno didn't have, we've sorted out more or less. So a very secret part of me, which no longer, I guess is not such a big secret since I'm saying it right now, which is that I wonder if number theory has something to contribute to this problem of infinity. So this is along the line of Noam's question. I do secretly hope that there might be such a thing. So that's one possible speculative answer. That somehow this Zeno's paradox problem of modern quantum field theory might be aided by number theory. But the other aspect is what I said at the beginning, that thinking about things like these horrible path integrals, seemingly horrible path integral, seem to have made enormous contributions to topology and algebraic geometry. So these little formulas that I'm showing you is an indication that number theory has something to gain by thinking about those things as well. So that's the other reason one might care about it. But of course, it's up to you.
Thanks so much, Minhyong. This was a great talk. And our next talk is on April 8th.